Well, that would have been disastrous. What? Okay. Hey, there we go. Perfecto. Hello, hello, hello. Oh, I don't want to do that. How's everybody doing today? I'm echoing. Hey, Dr. Dan, my dude, how are you? Hey, Brenton. I'm doing good, my dude. I'm doing very good. Hopefully you guys are doing well this morning. Make my thing a bit smaller. Hey, hello gamer. Hello, my fellow gamer. Right now, I'm not so much of a gamer. I'm just doing the things we gotta do. AKA, we gotta learn right now. How's it going today? Hopefully, everybody's doing well this morning. For me anyway. Let's get ready to rumble. You got that right. You gotta do it in your best Michael Buffer voice. You gotta do it's time. You know. Alrighty. We're gonna get started here in just a couple minutes, but yeah, it shouldn't be too bad this morning. So pretty nice and relaxed, I would have to say. Cool. Let's get ready to rumble, indeed. All right. Yes. Hopefully everybody had a good weekend. So, I had a nice relaxing weekend, just sitting and chilling, having a nice time. We ready? We ready for some? Ready for algebra today? I know that's not the most exciting question you've ever heard in your life, but that's what we're going to be doing. Focusing on here today is some algebra. So definitely on the docket here for today. Probably should get the word thing going. Get that there. All right. There we are. Perfecto. Angel. Go. All right, 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 all right. Yes, yes, yes. All right. See some people here in the chat. That's very good. All right, very, very good. All right, so I think it's a good time to go ahead and get started here. We'll have people come in when they are ready to go. I know it's a fresh week, so that's fine. We'll just go ahead and get going here, and hopefully we'll have the others join us in the meantime. All right, let's do this. Yes. Okay, let's get started today. Welcome back. Welcome back to Monday. Hopefully, you have a nice weekend. So today, we're going to be talking about Chapter 7 here, which is going to be all about algebra. Okay, algebra is going to be our main dude here today. So let's go ahead and talk about some of the things in regards to algebra. I'm going to turn down the volume of this music here so I can myself a bit make that like that. There we go. So we're going to be talking about the basics of algebra here today. We're going to be dealing with one-step, two-step problems. A lot of the things that we're going to be talking about here today will set us up for a lot of the things that we're going to be doing here in the next subsequent chapters. Now, Chapter 7 is pretty big, so we're going to kind of skim some topics here. We're not going to be going into too much detail in some sections. Just to let you know here, chapter 7 is we're only going to do like the first 6 sections. Yeah, the first 6 sections of chapter 7. So there's sections 7, 7, 7, 8. We're not going to be doing those at all. Okay, so you won't see any homework in regards to that. It'll just be the first 6 sections that I believe the homework will be covering. All right. In the meantime, however, let's go ahead and talk about a couple things here of what we'll need to do. We took a look at this kind of last week as well. We kind of had a good little preview in um, one of our word problems there. So when we took a look at some of those word problems there from last Friday, we took a look at a preview there on one of those particular questions. And so we're going to kind of expand on that here today in these questions as well, as you can see up here on the screen. Okay, so let's go ahead and take a look here and see what we get. All right, let's do it. All right, now let's take a good look here at algebra. How does it work with algebra here? Now, algebra could have formulas associated with it and whatnot, but we want to talk about how we're going to deal with algebraic expressions. All right, so we'll go with, it says algebraic language and formulas, but I'm just going to call it dealing with algebraic, uh, formulas, really, and expressions. So let's talk about the key to algebra. All right, so let's talk about the key to algebra. Does anybody remember? I probably did mention this before. Does anybody remember here? What was the key to algebra? What was the biggest key to algebra here in this case? Anybody remember the biggest key to algebra there? It's okay if you don't remember, but that's okay. It's no big deal. All right. Well, let's talk about our key to algebra if you're not sure. The key to algebra always goes and revolves around one word, and that is the word balance. Everything in algebra here revolves around the word balance. If you don't understand the word balance, well then math and algebra, they're not going to be your best friends. They're going to be your worst enemies. Balance is one of the biggest keys here in algebra that you can ever learn. Now, how does it work? Well, what do I mean by balance here? Well, we're going to take a look at how balance works here today in the probably the last couple sections we'll look at here today. But let's take a look here on how balance can work here at the very least in this first section. So let's look at an example here. Okay, let's take a good look here at, sure. Let's take a look at an electronics problem here. Make this a tad bit bigger. Oh, there we are. Okay, so let's look at this, let's look at number 2 here. Okay, so the current in amperes is in a simple electrical circuit is given by Ohm's law, which is I is equal to V over R, where V is the voltage and R is the resistance of the circuit. Find the current in the circuit whose resistance is 10 ohms that is connected across a 120 volt power source. Okay, let's talk about, in this case here, a few things. Now, let's go ahead and take out our paint tool for this one, because there's certain things that I do want to reflect here and certain things that I do want to actually say. Okay, let's go ahead and put down Ohm's law here first and foremost. All right, so we're given the fact that I here is equal to V over R. Okay, now one thing that's going to be important, guys, to know here about how it works is how do we go ahead and look at these formulas here. Now, one of the things that's important here, let's we did talk about this a while ago, and we've used it in several problems. Let's talk about one of the first keys here. So key number 1 is to note uh, what each letter in the formula means. Okay. We have to note what each letter in the formula means. So basically, if we look at a problem like this, all right, and we want to find out, hey, what does this mean here in particular? Okay, what does this mean in particular? Well, I'm given the fact that V here is the voltage and R here is the resistance. So V is voltage and R here is resistance. Okay, and we're also given I here, which is the current in amps. Okay. Okay. Now, let's take a good look here at a couple of other things. Hey, St. Just Germany, my dude. How are you doing, my friend? I hope you are well. Um, okay. Well, Good, good. How are things? How are things in your neck of the woods? Doing well? Hopefully they are. Let's talk about key number 2 here. All right, key number 2 is of course make note of the units associated with each letter. Okay, so for example here, voltage would be in volts, resistance would be in ohms, and I was the current in amps. So again, this would get volts. There we get ohms. Now, again, some problems do throw you a curveball where you don't have necessarily these 3 units necessarily given to you in the problem. So yeah, just have to make note and be sure that you just keep a sharp eye out in case if the problem just throws you that kind of curveball. Can you ask me a philosophical question about math? Sure, go ahead, my friend. My friend, absolutely, go for it. We make mathematical discoveries, not mathematical inventions. Continue making advances in our understanding of mathematics, like a jigsaw players piecing it all together. What's my take on that? Well, if I were to be perfectly honest, my take on that would be, um, if you look at the sciences as a whole, because you can make that you can make that not assumption, you can make that argument here for pretty much every science, where you have a set structure, but you don't know all the pieces of that set structure. So if you take a look at it from a point of view, is like, okay, um, human knowledge in terms of how it's evolved over the past, thousands and thousands of years, has come up to this point. And yes, we're continually making advances. Those advances in mathematics are fairly small, but they all start putting the pieces together here into understanding even more about, how, the universe works and how say certain aspects of things, how they kind of turn on its head. Don't forget though, mathematics is a construct. It's a construct that's understood by society, okay, in this case human society, all right, where it's accepted in every form and facet. But the more we start, kind of putting those pieces together per se, um, the more we start to understand how much of an importance that construct is, and how much we can actually change that if there's something that does change the game. And there have been plenty of proofs and theorems and along the way in the past thousands of years that certainly has changed the game. So I would say, unsolvable problems have become solvable. How can we apply that to something more something relevant toward other fields? That's also what mathematics is actually useful for. Um, so yes, if I were to even extrapolate that further, be like, hey, a jigsaw player, I would say that's the same piece that you could fit in any other science or any other field. How can we use that to to better humanity and its understanding of everything that's around us? That's fairly difficult, but it is doable. So I do like that quote. That quote's very good. Not so much of a discovery; it's just so much of as putting the pattern and pieces together. Yeah, very accurate. But that's my take on that. To be fair. Alrighty. You could let me know what you thought there. I know it's a little bit of a ramble, but apologies. Okay. All right. So we have I is equal to V over R. And let's go ahead and take a look here at the end of this problem here. Here again, we're given a resistance of 10 and a volt power source of 120. Now here comes the other part of this problem here that is equally as important. So let's put this in here. We got the voltage here of 120 and the resistance here of 10 ohms. Okay, now if you take a look at what I did here, I put those numbers there in parentheses. Let's talk about that here. This is one of the other keys to algebra that is very important. So always put parentheses around anything you substitute. This is probably one of the more important things here. And the reason why I put this here is always put parentheses around anything you substitute. The specific reason why I put that there is because of the fact that you could have numbers that have different signs, for example, like we saw in chapter 6. What if they were sign numbers? What if they were positive, negative numbers? Well, since you could change sign in a formula, whatever that formula is, doesn't really matter. But whatever that formula is, then it's good that we put parentheses around that just in case of sign changes. Now, I know it seems like really, like I said, a little asinine to do that here, but I do that because, again, we'll see examples later on where that may be the case. Okay, we may need to keep our things organized as best as possible. All right, so here our final answer here is going to be 12, and so here we get 12 amps. All right. Okay, are there any questions about that? No. Okay, let's hope that that works there. All right. In any case, let's go ahead and do the next one here. Okay. Do next. Okay, let's do that next one here. Go and find that dude. Okay, so let's look at number 8. Okay, so the volume of a round steel bar depends on its length L and diameter D according to the formula B is equal to pi times D squared times L all divided by 4. Find the volume of a bar 20 inches long and 3 inches in diameter. Round to the nearest 10 cubic inches. All right. So let's give it a try here. Again, what we're doing here is not, like I said, it's not super difficult. It's just a matter of just putting in those numbers in the right places and just getting our answer here. So again, this will also kind of rely on that as well. So let's put down our formula here. So, I mean, you have to think of it this way. I mean, they are separate subjects because you can certainly extend those into different fields, Germany. But let's not forget that math is a foundation, okay? So think of it this way. If you can't do anything further advanced without understanding the fundamentals. So think of math as like the fundamentals base part of the pyramid, whereas other subjects build upon that pyramid and can extend further from that. So um, yeah, there's not much left without the mathematics. That's very true. So I mean, but I would say math. Okay, science. The other sciences depend on a lot of math to extrapolate a lot of different data and make proper interpretations. Regardless of what science that you're looking at there. But I would say the difference between math and other sciences is that math is kind of the bedrock, and then the other sciences is just basically building on top of that bedrock. Much akin to like what ancient civilizations used to do is instead of like building a temple, a separate temple, they would build on top of another temple, and then they would use the existing structure as a way to kind of hold as a foundation for their new structure. So um, some places, so something akin to that, if you want to kind of call it that. All right, let's take a good look here at this next one. I have not heard of that, no. First time I've heard of that word. Well, I gotta do this problem here. So let's go ahead and do this here really quick. Okay, so we have to find the volume of this round steel bar depending on its length. So L here will be length. And D here will be diameter. Okay, so can anybody tell me what would L be and what would D be here in this case? What is L and what is D? No, it's okay. It's okay, Germany. I appreciate that. I just have to keep moving, that's all. I do apologize. I don't want to be rude to you. I will say this, other sciences that are out there, like psychological sciences, to be fair, psychological sciences, they do take a lot of trial and error. So, I mean, things that are a little bit more subjective like that, they built off of a mathematical concept, say, probability, studies and probabilities, but they also rely on a lot of observation as well. So, it's not as much math, of course, involved in sciences such as that. But again, it does have its purpose. Again, you use it as a fundamental, you use it as a base, but it's not like the full base. So I understand that some sciences they don't use math as a full base, but yeah. L is 3 and D is 3.14. L is 3. L is the length here. So how long is the bar here? D, unfortunately, is not 3.14. That's going to be pi there, Brenton. So pi is 3.14 according to this problem here, though I don't like using 3.14, admittingly. Why don't we try that once again? Then another go. I agree that those numbers will be involved for sure. I just want to be able to read this carefully here. All right. What does that say? It says we want to find the volume of a length of a bar 20 inches long. So what would 20 inches long be referring to there then? All right, very good. L is 20. Spot on. I agree with that, Brenton. Absolutely, 100%. So L is 20. What would 3 be? What would 3 be then? Uh, okay. That would be our diameter D, correct? Okay, good. Okay, good. Now let's go ahead and plug in our numbers here. So we have, let's go ahead and see what we got here. So we got V here is equal to pi times 3 squared. Notice again, I'm putting 3 in parentheses. L, which is 20, and I put that over 4. Again, I just fully expect you to use the calculator for this part here. But remember, as you can see here, we have 3 squared here, so right? So don't forget to put that down here. We'll go ahead and put, again, all right, so I use the exact value of pi here in this case. So here we got 141.37, something. Yeah, it's pretty accurate. All right, we got 141.37 would be our exact final answer for this. And there we go. Got it. All right, any questions about that? I should probably move that up. My face needs to keep it up. Yeah, there we go. All right, there we go. Okay, here we are. Okay, no questions? All right, let's move forward then. Let's try another. Let's try another. Bam. All right. What I wanna do. All right, here we go. Let's try one more here, and then we'll move to the next section here. One of these. Okay. Go ahead and do that one here. Let's do 28. This next. Oh, maybe not. Oh, that's on that page. Okay. Okay. So again, another machine trades here. So let's take a good look at this one. How many minutes will it take to lathe for a lathe to make 17 cuts, each 24.5 inches in length, on a steel shaft if the tool feed F is 0.065 inches per revolution and the shaft turns at 163 revolutions per minute? Use the formula T is equal to ln over Fr, where T is the cutting time, N is the number of cuts, L is the length of the cut, and F is the tool feed rate, inches per revolution, and R is the RPM rate of the workpiece. Okay. So lots of letters floating around here. Now this is again a good example of a problem where again just writing down each one of the things that's offered to you here, just organizing your thoughts here is fairly helpful. So let's write down the formula here in this case, and I'll put it over here. So we have T here is equal to ln over fr. Well, that's what it gives us here. And let's go ahead and define each one of these variables, okay? Each one of these letters here. So again, L here, see what L represents. L is the length of the cut, okay? So length of cut. All right, so that's the length of the cut. All right, N here is going to be, let's see here, N is the number of cuts. So don't know if you have the number of cuts. All right. Next one here is going to be, let's see, F. F is the feed rate. So F is the feed rate, the tool feed rate. And R here specifically, R here is the RPM of the workpiece. Okay, so RPM. All right, so we got all the letters here represented in some way, shape, or form. Now that we know what each letter means, all right, take a look here very carefully at each one. There's one of them already kind of given to us. So F here is given to us as 0.065. So we can take that to the bank here. This is going to be 0.065. That's just given to us outright here in the problem. But how about the other letters here in this case? Okay, how about the other letters here in this case? What would they be? So what would the other letters be in this problem according to what you see on the screen? L is 24.5. Okay, agreed with that. That's definitely true. All right. How about N and R? So N is 17. All right, spot on. That's true. N is 17. That's the number of cuts. What about R here? Well, that's the last one here. 163. Excellent. All right. That's right. So you can see here that at least writing out what each letter means and just keeping yourself organized makes it a lot easier for us to just kind of plop in the numbers here where they're needed in order for us to solve for this final, this final result. Again, that's the whole goal behind these problems here is just to get you comfortable with the ideas like, okay, if you're given a formula here, then how do you be able to apply that? Well, you can directly apply it here by just first knowing what each letter means and then just applying it appropriately. Well, let's go ahead and put in some numbers here. So we have L here, which is 24.5. So 24.5, 24.5. We have N here, which was correctly stated as 17. It's the number of cuts. We're going to divide that by 0.065 times 163. Okay. All right. And do we have an answer for this one here? I'm going to make this bigger here. Just erase all this junk. Do we have an answer for this? Again, you put this in your calculator here. So again, make sure if you're going to put this in the calculator here, make sure you put parentheses around this bottom part here. So just be careful about that. So, okay, that's correct. Very good. Nice. So 39.31. We'll put 311. All right, sure. All right, nice job. All right, easy peasy. Okay, any questions about that? Did it ask us to round? I guess it just depends if it asks us to round or not. I don't know if it did, but let's check. Round to the nearest minute. Okay, so if we round it to the nearest minute here, what would this be close to? 39 minutes? So 39 minutes. If it was rounded according to the problem here. So you'd be like about 39 minutes to be fair. Since that's what it asked us to do. So meh. All right. Any questions about this first section here? This is pretty much like there's a lot of different problems here in this section, but they all boil down to the same exact element that you see here in these three examples. You're given a formula, you plop numbers in where they need to go, and then you solve. And then that's it. That's all you have to do. There's not much to it outside of that. Okay. No? Okay. You just check something here. There we go. There we go. That'll be okay. Wait, what? Oh no. Oh, yeah. Hey, you saw me. Hey, no problem, Tyler. I'm gonna be happy to. Charlie Morley is a very nice dude. He's also a mod here on my channel. A very nice dude. Appreciate you, buddy. No questions from you? Okay. Need to check something here. Let's see if this works. I get this? No? I'm gonna have to set this up here. I'm trying to set up Nightbot. See if this works. So, the show of a game. Nope. Okay. That don't work either. I probably should add this in there eventually. Nope. Let's try this here. All right, so it looks like I'll have to link that. All right. I'm just trying to get like a rules thing going, so that way, Nightbot just kind of does my modding for me. All right, had to try that out. All right. In any case, let's move on here. Always trying something new to enhance the channel, you know. So it's a bit easier for me to manage. All right. In any case, let's look at section 7.2. Okay, so let's look at section 7.2 here. All right. So section 7.2 here is going to be basically adding and subtracting algebraic expressions. So in a sense, basically, what's this talking about here? Not that. That's not what I clicked on. Basically, what's this essentially talking about here? I think I have to create the command. I think I do. I think that's true. I think that's true. Like, I'm really bad at this, so. Oh, okay. So I have to. All right. Let's see if this works, ladies and gentlemen. I'm gonna try it out here. This basically says. Let's see if this works. Hey, it's Jeremy. How are you, my dude? Probably do have to create the command somehow. Well, I guess I'll have to figure that out. I thought that was okay. So, yeah. Let's see if this works here. Okay, good. That works. Hey, all right. Good job, Nightbot. You the best. Now I gotta readjust your timers, and now you're working. Okay. Okay. There we go. Perfect. All right. That should help for the modding part there. Excellent. I'm so old. All right. So let's talk about like terms here. And this is a pretty short section here. So we're not going to spend too much time on this in all honesty. Okay. Now, of course, this looks like a whole jumble of letters. And really, in reality, it kind of is. But we need to talk about exactly what we're looking at here and, things like this. So let's take a good look here. This is not too hard, though. What we want to talk about here is like terms. All right. So like terms here is something that we want to look at here. We're going to be able to combine like terms depending on the expression that we're given here. In a sense, all like terms are basically, so basically you can add or subtract like terms. So basically they're terms that have the same exact letter or letters and same exact powers for those letters. Okay? So understand that like terms are terms that have same exact letter or letters or same exact powers for those letters. So in a sense here, let's take a look here at how this works. All right. So if I have, say, 5x plus 2x, Okay, are these like terms? Is 5x and 2x, can I actually add these together? I guess is the base question here. Is it possible for me to add this together? Yes? Let's take a look here. So notice that we have the same letter in each one. We have an x and we have an x. And they are the same power. This would be like x to the first, and this would also be x to the first. So the same exact letters, as you can see here, and the same exact power. So let's make a note about this here. That way we're keep in mind here. Note, the number in front of the letter does not matter when determining like terms. Okay, so the 5 and the 2, we can go ahead and add those together there once we determine that they're like terms. Okay, but in terms of just saying, oh, is 5x and 2x like terms? The answer is yes, they are indeed like terms. Now, all we have to do is, if we're going to add these like terms here together, is we take 5x plus 2x, we just take 5 plus 2, which is 7, and we take 7x here. So let's talk about one of the most important keys here, so that way it's there's less confusion here. Key here is to keep the letter the same, okay, with its respective power. So meaning to say, notice I didn't make this 7x squared, okay? I just made this 7x. All right, so if I'm going to add these two things together here, I add the 5 and the 2 together, which is 7, and then I just leave the x alone. Okay, I just plop it in x, and that's it. Not actually, combining the x's like that. Okay. So let's understand here that we want to go ahead and be able to do that here for a lot of these type of problems. Let's look at another one though. Okay. Let's try this one here. Let's try this here. Put this on the little paint tool here. So really quick, really fast one here. How about are these like terms? I have 2x minus 3x squared. Are these like terms? Yes or no? So 2x minus 3x squared. So let's take a look at those two. Is 2x and 3x squared, are those like terms? Yes or no? Look at it carefully, Brenton. Look at what the definition of a like term is. I can't simplify that. Okay. So why not? Why can't I simplify that? Why are they not like terms? Why are they not like terms? Wait, you can? They're the same like terms. All right, let's read this. Let's read this definition again, everybody. Read this definition again. What does that say? You have the same exact letters and same exact powers for those letters. So do we have the same exact letters here? Let's answer this question here, okay? Let's go one at a time. All right? Do we have the same exact letters? So yes or no, do we have the same exact letters? Do we have an X in both of them? Yes, but different powers. That's correct. Okay? So we have the same exact letters here of X and X, but we do not have the same exact powers for those letters. Hey, Connor, how you doing, buddy? So this is X to the first, this is X to the second. Those are different powers there, so we cannot combine those. These are not like terms. Okay, these are not like terms. All right. So I cannot combine these together because unfortunately one of them is x squared and the other one is just x. So unfortunately those violate the definition here. Remember, it has to satisfy both of these. Okay? It can't satisfy one and then you can call it good. You have to satisfy both or it fails. Right on, brother. I can respect that. What time is it over in Ireland? I don't know. All right, let's try 4:52. Okay, so you're streaming in a couple hours. All right, no problem. Streaming a couple hours. It's about it's a little bit close to 11 a.m. right over here in the Midwest. So are these like terms? Is 2y minus 5y? So let's take a look at that. Are these like terms? Is 2y and 5y, are they like terms? Okay, yes. So we can combine these. Yes. Okay, good. So what's 2 minus 5? What do we get here? So what is 2 minus 5 here? Minus 3. Good. So all we're going to have here is we're just going to get minus 3y. Remember, we just leave the y alone. Just keep it as is. All right? Nice. Good job, everybody. Nice job, Connor. Good job, Selena. All right. All right. Questions about that? Let's go ahead and try some other problems here. Okay. Like terms in the letter after the number is the same. X squared and x. Yeah, that's correct. However, However, one thing that you can say about like terms here, Connor, is that if you have, say, 2xy, let's call it 3xy, minus, let's say, 2yx, these two are like terms as well. Okay, so this, x, y, and yx, they are like terms. Again, that's why I look at the definition. What letters do you have? Well, you have x and y in both. Okay, so they're satisfied. You have x in this first one, you have x in the second one. You have y in the first one, you have y in the second one. Well, what are the powers of those letters? Okay, well, we got x to the first, we got x to the first there. We have y, we have y. Okay, perfect. So these are like terms. And then you can combine them together. However, if I change this just a slight bit, if I made this 2y squared x, these are not like terms. That's the big key difference here, is that here you have a y squared. You have the same letters of x and y, but one is y squared now. Order doesn't matter, but power does. Correct. That is correct. The power of each letter does matter. However, the order in which those letters are written do not matter. So you could see some problems that could throw you some curveballs just like that and be like, okay, well, how do I handle that? Well, just look at the definition here, the base definition here, same exact letters and same exact powers. That's my math worked. Glad I could be of some help. It really isn't that hard apart from that. There's a couple of other things, though, that you do have to be a little bit aware of. Let's take a look at some problems in relation to that, though. Maybe just a couple of small details. Uh, let's take a look at some problems here and talk about how we can combine these together. So fundamentally, they're not too hard. It's just a matter of getting it down. All right. All right. Here's the next one. Here we have minus, and then we have 3 plus 5m plus the quantity of 11 minus 4m. Okay, so one of the things that you want to do here is remember with this minus sign out front, all right, you're going to distribute this minus sign here to both terms inside the parentheses. So you're going to take, like, you can think of the minus sign as saying minus 1 and multiplying minus 1 by both the things on the inside here. So what we'll get is we're going to get minus 3 minus 5m. Okay, just be careful of the sign change here. Plus 11 minus 4m, since we're just adding straight up. Okay. And let's take a good look here on what we can combine. As you can see here, we can combine the minus 3 and the 11. Okay, because those are numbers we could just plain add together. No problemo. And so here we get minus 3 plus 11 is positive 8. All right. Now, let's take a look at the other one here. So that's rose and that's pink. Pink looks like purple. Anyway, so we have minus 5m and minus 4m. Are those like terms? Is minus 5m and minus 4m like terms? Yes. Okay, and adding them together, we get minus 5 minus 4. So this is going to be minus 5m minus 4m. That's going to be minus 9m. All right, and that's our final answer for that. Cool. Any questions about that? You got to be careful about the really. You got to just be careful about the subtleties there. Let's go ahead and look at another one here, though. Subtleties in math are always the thing. Yeah. Now there won't be like terms in this problem here because everything's kind of separate. But I do want to point out one important thing here. So we got 6 minus 2 times the quantity 3a minus 5b. Now none of these are like terms because we have 1a, we have 1b, and we got one regular number. All right, so there's not anything that we're going to combine here at the end. The important point that I want to make here in a problem like this specifically is you see here we have a minus 2. So just like the last problem, we had a minus 1 here. This minus 2 is still going to be distributed to both terms. So I guess the one thing is that, just note here, watch out for sign changes after multiplying or distributing, I should say. So that's one of the things that I kind of stress here a lot. And I see like, oh, seems so silly, but I'm like, yeah, I can't tell you how many times I look at papers and be like, oh my gosh, what happened to my life? All right, so I don't want to be like, So here we get 6. We distribute the minus 2 here to both ones. So we have negative 2 times 3a, which is minus 6a. Okay, negative 2 times positive 3. A negative times a positive is a negative. And negative 2 times negative 5, which is positive 10, and then with a b kind of tacked on at the end there. And that's correct. JC, that's correct. So 6 minus 6a plus 10b is your correct answer. All right, cool beans. All right, are there any questions about that? I want to be sure that we went over that just briefly, and then you guys can see what we kind of did with that. So hopefully that isn't super hard. All right. Let's take a look here at the next section. All right. That's okay. Fine. That's okay. All right. So let's look at this section here for, I think, yeah, so I kind of figure that out there. Think about that for a second. Yeah. Okay. Yeah. All right. That's what I want to do here. All right. That's fine. Do I want to do that here? Okay. I guess I do. Yep. All right. We'll make that. Solving one-step equations. All right. So in this next section here, sorry, I was just kind of mulling which way I wanted to kind of go here. What I wanted to do next. I do want to do this section. I was just thinking if I should do the next section after that, but I think we'll do. Let me get you guys' opinion here. you guys want this as the last section for today, or do you want me to do section 7.4 as well? You guys tell me what you'd like to do. You guys let me know which way you guys want to go. I'm kind of debating it myself, but today's been a little slow, so I don't know if you guys are tired or whatnot, but that's why I'm asking. What would you guys want to do? I need a little bit more of a firm answer, Brenton. No with a question mark doesn't mean much. No? Doesn't matter? Okay. All right. Well, that should be fine then. All right. Make this, you could do more notes? Okay, good. All right. We'll go with that. All right. So let's take a good look here at section 7.3 then. We're going to solve one-step equations. All right. So as I mentioned here before, the key here is just going to revolve around balance. All right. Everything here is a balance. Everything we're going to do is a balance here in this section. And we're going to be able to solve for certain equations here doing one-step problems. Again, we're just going to be wanting to solve for a particular variable given the formula here in the problem and some information. All right, very good. Okay. What the? Okay, that was weird. Okay, let's take a good look here at our guy here, and we're going to look at the next section here. Tear this down. All right, so let me go to the necessary page here. This is going to be on page 458. All right. Let's take a good look here at number 1. All right. We'll do another Ohm's law problem here. So number 1, Ohm's law is often written in the form I is equal to E over R, where I is the current in amps, E is the voltage, and R is the resistance in ohms. What is the voltage necessary to push a 0.80 amp current through a resistance of 450 ohms? Now, like we talked about here in the first section says, okay, we need to know where these numbers need to go specifically. Okay, so if we need to know where these numbers go, okay, let's first write out our formula here in this problem. So our formula here specifically is going to be I is equal to E over R. And let's see what numbers we're given here in a problem like this. We know that I here is the current amps, E is the voltage, and R is the resistance according to the problem. We're given the fact that we're trying to push a 0.80 amp current, so that's going to be I. So I here is going to be 0.80. And this is going to equal E, which is our voltage here. We don't know what our voltage is because that's what we're trying to find. It says what is the voltage, and we're given a resistance here of 450. Okay, so this is what we have here so far in terms of the numbers that were given. Okay, now our goal here is to get e by itself, okay? That's the goal. Goal is to get e by itself. Now, in order for us to get e by itself, let's take a look at the roadblocks that are in the way, or in this case, just a roadblock. So the roadblock that's in the way here is that I got this 450 kind of sitting down here. I said, okay, this 450 is kind of in my way. I don't really like that. So if I have e divided by 450, and so what I need to do is I need to get rid of that 450, but I'm dividing again because I want to get rid of that 450 here. I don't want to see it anymore on this side of the equation, so I can get e alone by itself. So since I have e divided by 450, I do the opposite of division. And what's the opposite of division? What's the opposite of division here? No, it seems a little silly, but still. All right, right, multiplication. Very good. Okay, good, nice. So we're going to multiply by 450 on both sides. That's right. So if we multiply by 450, that will cancel out these 450. Again, I just do the opposite here. But of course, since everything is a balance in this, when it comes to this step problems here, that's why I multiply this by 450 as well. So I get 450 on both sides just like so. And then of course, you can use your calculator to multiply by 450. And anybody tell me what the answer we get here is? So what's our answer for this problem? 360. All right, good. Nice. So our final answer here is going to be, our number of volts is going to have to be 360. All right. All right. I don't know if how big of a delay there is, but it seems like there's a large delay between you guys answering and stuff. So not sure why. Usually I expect these delays to be much shorter, but well, that's okay. I guess we'll figure it out. All right, let's look at the next one. All right. Okay, let's look at one more here in this section. There's not a lot in this section, just a matter of just getting that one step down. Actually, that's not bad. Okay, yeah, we could do that. All right. Let's take a good look here at number 11. Okay, so number 11 says, business and finance, the formula for a company's net profit margin, M, expressed as a percent, is given by M is equal to 100 I over R, where I represents the net income and R represents the net revenue. If a company had a net profit margin of 2.85% on net revenue of 4,625,000, what was its net income? Round the nearest $100. Okay, let's go ahead and write down our formula here for this one. Okay. All right. So for this one here specifically, let's at least knowing the context of each of the letters here is going to prove to be very helpful. So again, here M is going to be the rate, I guess this case here, the profit margin, I guess I should say, percent profit margin. And then we're given here I is going to represent net income and net revenue. Okay, so I, net income, and R is net revenue. Okay, now that we have that, let's go ahead and take a look and put in our numbers here respectively in this formula. So we're given, actually I'll move it over here. So we're given here, probably do need to make this smaller because I'm having a hard time with this. All right, let's try it now. That works. That works slightly a bit better. So, all right, I'll take that. Okay, so we're given here 2.85%, and we're given a net revenue of $4.625 million. Okay, so we have 2.85%, so 2.85 equals 100I over 4.625 million. Okay, this will actually be a really good example for a two-step problem here. So can anybody tell me here, what should we do first here? What should we do first here in this problem? We want to solve for I. So what should we do first? What do you think is a good idea? What do you think we should do first here? Okay, yeah, that's right, JC. Let's do that first. All right, so let's multiply by 4.625 million here. Okay, that's right. Okay, I agree with everything here. So again, we got roadblocks in our way. The first roadblock we can clearly see is the 4 million. So we're just going to multiply that on both sides, again, keeping the balance. Everything is balance, balance, and more balance. So we're just doing balancy stuff. Okay, let's go ahead and multiply that here first. So probably going to be a silly amount. So yeah. Going to be a pretty absurd number here. But let's take a look at said absurd number. So this is what I have here so far. 1250. All right. All right. And what should we do next? What should we do next then? We still need to solve for I. So what's our next step? Probably this could potentially be a one-step operation, but two steps makes this significantly easier. So Yeah, let's divide by 100 on both sides. That's right. So if we divide by 100 here, again, our roadblock here is the 100. It's being multiplied by I, so we do the opposite, and we divide by 100 here. And then we'll get our final answer for this problem here. So we get 131,812. 0.5. Okay. Okay. Good stuff. All right. Any questions about that? Hopefully that's not too bad. All right. Okay. Let's go ahead and do another few examples here, but this time let's go to the next section over. All right. So let's go over to section 7.4. So section 7.4 is basically doing what we did in the last example and solving two-step equations. There's literally no difference here. Again, we just think about balance. Always think about balance. To get what you want. All right. So that's the big key here in all caps. Always think about balance to get what you want. All right. So let's look at some problems here and let's see how we can do some two-step problems here. All right. And we'll see how it works. Okay. All right. Let's take a look here. This will be our All right, let's take a look here at a couple of these. Let's look at this first one here. Number 1, office services. A repair service charges 45 bucks for a house call and an additional 60 bucks per hour of work. The formula of T is equal to 45 plus 60H represents the total charge T for H hours of work. If the total bill for a customer was $375, how many hours of actual labor were there? Okay, so in this case here, T is the total charge for this particular office service. All right. So in this instance, T here is equal to 45 plus 60H. And our total bill here for the customer was $375. So 375 was equal to T. So we're going to plug that in right in for that T right there. So that's where I was substituting here. 375 equals 45 plus 60H. All right. Now we just want to take a couple of steps here to get H by itself. Again, same goal, same everything. What do you think we could do here first? What should we do here first in this case? How do we solve for H here? Okay, very good. That's right. So we're going to subtract by 45. Again, that's the first roadblock here in this case. We're going to subtract by 45 here in both cases. Let's take it one step at a time here. So here we want to subtract first 375 minus 45, and that equals 60h. Then as you can see here, we are multiplying 60 times h. So we want to divide by 60 on both sides here, so that way we get h by itself. And what do we get for h here? What does h equal to? Five and a half. Okay, very good. Nice job. All right, not too shabby. Pretty straightforward. Yeah, these problems here are super straightforward. Like they don't require too much effort here. It's just a matter of just getting the numbers in the right places and then moving stuff over. Really not too bad. There's not much in this section here, so I wanna do which one I wanna do next. Yes, that one's actually really good. Couple of practical things. All right, let's look at that one here. This will be our final example here for today. So let's look at this one. All right. So this one here doesn't really have a formula, but let's talk about how we can solve for this. General interest. A student has a test average of 89.4 for the first 5 tests of the semester. What score would the student need on the 6th test in order to achieve an average of 90 for all 6 tests? Okay. So the first 5 tests, the average of 89.4%. Super exact, but okay. Then needs to score some kind of magical score here and say, all right, I'm gonna need a 90 average overall. Okay. So let's take a look at how we can do that here in this case. Okay. So if we average a 90 for all 6 tests, let's look at it that way. We have to average a 90 for all 6 tests. How many points do we need for all 6 tests to average a 90? So how many total points from all the tests do we need to average a 90 over 6 tests? That's really the big crux here of the problem, is just at least understanding that. How many total points from all the tests do we need there to average a 90 over all 6 tests? What do you guys think? How do you think that'll work? So the way we want to think about it is, if I want an average of 90 on every test, okay, imagine if I got a 90 on every test, okay, I got a 90, 90, 90, 90, 90, right? If I average a 90 on every test, then I just multiply that by 6. So the amount of points I should have after the end of after the end of the day should be 540 points. Okay. That's how many points I need overall in order to average a 90%. What I do know is that the first 5 tests, I've averaged 89.4 points. So those are from the first 5 tests. And then I need to add the last remaining test, which is x, and that somehow magically equals 540. Okay, so let's go ahead and met this out here. We do 89.4 times 5. So here we get 447 plus x equals 540. Okay, we just go ahead and subtract by 447. So let's subtract by 447. All right, so I get 540 minus 447, and if I subtract that, I finally get 93. Should be my amount of points I need to get on my final test to average a 90. Okay? Are there any questions about that? No? Okay. Good. So that's talking about two-step problems there. We may start with an example here for next time, but it's not too bad. All right. Very good job here today, everybody. I know it's a little bit slow here today. Maybe it's just because it's Monday. I don't know. I don't know if it's because it's Mondays, but hopefully we'll be on the ball here for Wednesday. Okay, so that takes care of the first 4 sections here of Chapter 7. We're going to finish up Chapter 7 here for next time, and then we'll get started here with Chapter 8 as well. Just to let you know here, just a friendly reminder, remember that not this Wednesday, but the following Wednesday, we will not be meeting here the following Wednesday because of Thanksgiving holiday. So don't forget about that. There will be no class here next Wednesday. That it will be on the 25th for Thanksgiving holiday. All right, so just give yourself a friendly reminder in regards to that. All right. All right, great job everybody here today. I want to thank you all very much for coming out here to the stream. I really appreciate the time and effort that you come out here for the stream. Hopefully we get to, we pick up the pace a little bit here. Hey, Brenton, do you want me to send you the notes here again? Yes? Okay. No problem. Will do, my friend. Will do. Absolutely. 100%. All right. Great. Okay. Okay. Well, nice work today, everybody. Again, appreciate your time for coming on out. Thank you again, and we will see you in a couple of days. All right. I will save this document here for you, Brenton, as always. All right. This is that's it. 16. All right. All right. All right. Take care, everybody, and we'll see you in a couple days, everybody. Have a great one.